Well, thanks everybody for coming. It's a long ways from the Midwest, I guess. My name is Jack Sowers. I work for Bay Road Drilling Fluids, the division of Halliburton. My colleague Kirby Donald was supposed to be here today, and he had a different engagement he had to go to, so I'm going to cover it. So, just a brief background on me. I'm an economic exploration geologist. Worked in the mining industry in Nevada and Arizona, Alaska, and the price of minerals. Gold goes up, copper goes up, and then it comes down. So there goes Jack getting laid off again. So I was at a mining conference, and a fellow I knew from New Mexico was they were going to start selling drilling fluids into the mining industry, and I thought I would do that for the time being until I found another job. Looking for minerals, but that was 35 years ago, so I've been with Bay Road that long, and I guess if I had to have a title, I'm a drilling fluids engineer, and we train the industry on, like we're going to talk about today, grout, drilling mud, and all the above. So we always, with our company, we always start with a safety moment. This is, it has to do with mixing grouts because we create some dust, so it's obviously it's a good idea to stand downwind or upwind from the mixing procedure. And there are those N95 respirators we all had to wear for a couple of years because it didn't filter out COVID by any means at all. So anyway, so they'll take it down to 0.3 microns, which is it's my micron is a millionth of a meter. Is that correct? So anyway, it's pretty fine. So why do we seal well? I got to looking at the presentation by Tom Christofferson. They did a grout study at the University of Nebraska a number of years ago. And first of all, it's legal that we comply with local and state regulations, and all the abandonment requirements. Somebody mentioned it a little bit ago that every state's a little bit different. I think Ben was saying that Idaho is different than Montana. For instance, in Idaho, when you're grouting, it's required a 30% solids grout. In most other states, Oregon, Washington, it's a 20% solids grout. So you got to know the local regulations. On a practical side, it provides casing support. It helps to safely seal the annular spaces. We don't want to have commingling of aquifers, what happens. And so it's practical, we safely fill an open borehole. And we'll get to that in a little bit, some of the methodologies here. So protecting the groundwater quality, I think in the Nebraska study, they had the nitrates were above, 10 milligrams per liter is the cutoff. So they were finding that was much higher, and the reason for that was because some of the wells that were sealed back in the 50s, instead of using a grout seal, like a bentonite seal or a cement seal, they just filled the backside with gravel, which provided an avenue for contamination from surface waters or different from farming activities from the nitrates and stuff. So we definitely want to keep the aquifers from commingling. So what we like to talk about is, we start a good seal with the first turn of the bit. So a little bit of planning, and we'll go over this as we go along. Geology, it's all different, right? We could be drilling in, overburden, alluvium. Problematic could be limestones. Or a lot of places in the western states, we have a lot of volcanics. The Vado zone is a seasonal variation of the water table which varies depending on the precipitation and droughts and all that kind of stuff. Are you going there? Okay. Oh, my gosh. Sorry. Okay, let's go back to where we were. Okay, with geology, Grout choice is influenced by geology. Like I said, we could have limestones, like karst topography, which are dissolution cavities in limestone, so that could affect our grout decisions. So one size doesn't fit all. So the vadose zone, this unsaturated zone between the piezometric level and the water table, or the ground surface and the water table. It's regionally influenced. Many of you know that we didn't have a lot of snow out west here this year, so we're going to be looking at probably extended vadose zones and probably drought conditions. And it usually fluctuates seasonally. And like I said, this year we're having a drought. Sometimes we'll have so much snowfall we don't know what to do with it. Sealing materials can desiccate and crack over time. And I think that's what in the grout study, they found that when pumpable grouts were placed in the vadose zone, well, they just disappeared, so they were able to mitigate that. Formation water chemistry. Excessive chlorides and total hardness can have a negative impact on a bentonite seal. Chlorides in excess of 1,500 ppm, which is basically salt. Total hardness of 500 ppm or milligrams per liter with combined calcium and magnesium. And having these both is cumulative effect. I was working in a job down in Dixie Valley, Nevada, and definitely wouldn't be good for bentonite. The chlorides were about 25,000 parts per million, and the total hardness is over 2,000. But in that case, we use cement. If your bentonite's not able to hydrate, it's contaminated. That will have an impact on hydration of the product and also the permeability, which won't not have a good seal. So well construction, we have case well, we have screens, we have slots, louvered, and also open hole construction. So basically the requirement of the seal is to seal the annular space between the casing and the borehole by replacing the native material with a product that meets or exceeds the sealing capacity of the formation. And just generally means that permeability of 1.0 times 10 to the minus 7 centimeters per second, or approximately 1.25 inches per year. Pretty low. So different types of sealing materials that we use. Calcium bentonite. There's a lot of bentonite around the world. It has a dominant calcium exchangeable ion. It's not a very good sealing. Normally these things are used for skincare products and different things like that. Sodium bentonite, definitely the best bentonite for sealing in the form of pumpable grouts, chips, and pellets. And then, of course, is our old friend cement. And Portland cement, kind of a blend of a cement and bentonite, which is pretty common, and also specialty cements. With calcium bentonite, we don't normally use it for sealing, so we're going to take that out of the equation. A lot of bentonite clays from around the world don't have the sealing capacity that sodium bentonite do. So what do? They enhance it, either with polymers or with soda ash to try to make it a better bentonite. But it's with a bentonite that's generally mined in Wyoming and Montana. I'll show you why. I'll tell you why we got lucky with the bentonite out here in Montana and Wyoming. It's basically it was a pulse. Anybody know about the Yellowstone hotspot? Anybody familiar with that? Yellowstone hotspot is basically it's a mantle plume that the continental United States is sliding to the southwest, and we started with volcanism basically from maybe Tillamook, Oregon, Smith Rock, McDermott, Nevada, all the way up to Burley, Idaho. So these pulses of volcanic ash were put into an inland sea, probably Gondwana land, or when the continents were all kind of maybe all stuck together. But we got the pulse, and there's no other bentonite in the world like it. So as this volcanic ash fell into this aquatic environment, subsequent, weathering and metamorphing of the clays, it turned the clays into a natural high sodium bentonite. Like I said, some of the other clays that are found around the world have to be benefacted with some sort of material, either with a polymer or something maybe like soda ash. So why use bentonite for a seal? It has the ability to hydrate and expand. So I used to be able to take it's like a 16-ounce cup of whole plug, what we would call bentonite chips, and add the same amount of water and seal that up in a 1 quart Ziploc freezer bag. And as the bentonite hydrated, it expanded, and it would actually break the seal that was on that 1 quart bag. That's kind of what we're looking for. It's expansion pressure, and it's also confining pressure. So we want a low permeability material, less than 1.0 times 10 to the minus 7 centimeters per second. Increased slurry volume over possibly like, using cement, for instance. Okay. It produces a flexible seal. Anybody, if you've ever seen bentonite, it's just like hard modeling clay. And there's no heat of hydration. And I'll explain that. Basically, when you're using the cement, as the cement cures, it's an exothermic reaction. So it gives off heat. And the heat can sometimes be excessive enough to where it's going to deform plastic pipe and also with steel pipe, because as the exothermic reaction goes, it gives off heat. So if you have steel pipe, it actually expands the steel a little bit, and as the cement cures, then the steel contracts. So there you have a microanalysis. So your seal isn't what you need it to be. So the high quality bentonite produces higher quality seals. Sodium bentonite superior to calcium bentonite. So the definition of high quality bentonite. It's a high percentage of sodium montmorillonite. And so montmorillonite, basically, it's a smectitic clay that actually expands. So it results in higher liquid limits, so it can take on more water to expand the structure, providing a higher expansion pressure. And so that's basically determined by analysis of untreated bentonite, XRD or one of the XRF. So it has a high shear strength and a high degree of confidence in the seal. This is just a little diagram here of the different types of sealing materials. We start off with the bentonite, and then we'll go to pumpable grouts. Pumpable grouts are convenient because you can actually place them down the annular space of the borehole without having to worry about bridging and leaving gaps in the seal itself. And of course, there's chips and there's pellets. They probably are, the bentonite chips are probably the best seal that's available out there, but there are some issues with actually getting a 3/8 inch material down, let's say a couple hundred feet without bridging off. Some states require that you actually tremie it down from the top of the gravel pack where your aquifer is or your producing zone is to the surface. Other states require that you maybe sieve out, because all bentonite is just clay and it gets moved around the bag, so you're going to have a dust issue in the bag. So some states require you to remove that dust by running across an expanded metal screen or something like that, because what that does is bentonite clay dust. And so what that's going to do, it's going to viscosify the water that's in the well, so it's going to impede the downward travel of the bentonite particles to depth, so you don't bridge off. And so we have inhibited grouts, dispersed grouts, pellets. Maybe some of you people have seen pellets. There's a company called, I think it's PDSCO, they take 30 mesh material and they squeeze it together for 3,500 PSI, and the inherent moisture content in the clay will create a nice little pretty pellet. And many engineering firms require them because, well, they're kind of pretty, you know, and they seem to pack really well. But if you consider it, it's a 30 mesh material versus a 3/8 inch solid piece of clay, the seal isn't probably going to be as good as a chip bentonite. And then we'll look at the cement. There's different types of cement. There's neat Portland cement, and then there's engineered cements. And engineered cements, maybe some of you are aware that because of different ideas with that, like heat of hydration, different things, a lot of engineer and hydrology firms will have you add bentonite to the cement. Bentonite doesn't benefact the cement at all. It actually has a higher water requirement. So in other words, it lightens the cement a little bit, and it also it pumps a little bit better. But because it has an additional water requirement, it's a slower set time, and the heat of hydration is not as high. And then of course, you know, when you mix cement the way Halliburton likes you to mix cement, a concentration of 5.2 gallons of water and 94-pound sack of cement, which is a cubic foot, cement can get a little thick. And if you don't have the proper equipment on the rig, then it's going to take too much time to pump the cement. It could go off down the hole, and it has other problems. But, I mean, we can address all those. Chip bentonite. Bentonite utilized in well completion abandonment. Best possible seal, highest percentage of solids, and the maximum structural integrity. Here again, you have to be able to get that bentonite down between your casing and the borehole. So it takes a while, and it takes a little bit of methodology to actually get it right. It's less susceptible to contaminants and subsidence, and it's the best bentonite choice in the vadose zone, as determined by the Nebraska grout study. It was unconditionally that was the best. It requires adequate annular space and proper installation methods. So, in general, we like to say 2 to 3 minutes a sack. But I've done that. I've been in core holes in Nevada, and we put the timer on, and we try to mix 3 minutes per sack, and you had to put like 50 sacks down the hole. Well, it wasn't pretty. So, well, we cheated a little bit. So, and it's recommended above the filter pack where your shale trap is to kind of put a certain thickness of bentonite on top of that before you start. You may be possibly using either cement or pumpable grouts. And there again, 1.5 times 10 to the minus 9 permeability. So here's a little couple of pictures here of a device to where you could actually put the chip bentonite across that expanded metal screen, and if there's any dust in the sack, then that's removed before it starts traveling down. Like I said, bentonite is a viscosifier, so if you viscosify the water that's in your annular space, it will slow the migration of the bentonite down to the bottom of the hole, which could cause bridging, which could cause not a very good seal. And I've seen quite a few of these different types of devices, anything made out of sewer pipe or whatever, but just to get the dust out, and then if you can kind of figure out 2 to 3 minutes per sack to put that down the hole. And there's another thing, probably maybe I'll talk about it here in a minute, but you should know what the approximate amount of volume you have in the hole. And so we know that 1 sack of granular bentonite, the 3/8 size, is roughly 0.7 cubic feet. So if you know your approximate amount of material that you need and you use half of it, I'd say you've got a problem somewhere. So it's likely a bridge. So bentonite pellets, like I said, they're 30 mesh material, squeezed together. probably 3,500 PSI, and they come in different sizes. I think quarter, 3/8, and maybe half-inch. A high percentage of solids, and they're usually specified by the client. Now, they're kind of expensive, and so if the client's willing to pay for them, I guess that's kind of what's important. Yeah, but they don't have the structural integrity that does have of chips, because when they hydrate, now you have 30 mesh material rather than a massive chunk of clay. So there's two different kinds. There's untreated compressed bentonite, which will probably go off a little faster, and they're probably a lot less money than the coated pellets are, and they're quite a bit more than chips. Okay, and can be problematic in emplacement, because if they start to, especially uncoated pellets, the water starts hydrating them, and the likelihood of them bridging off the annular space it's there. I don't know what time period that would be, but so like I mentioned, quarter, 3/8, and half-inch size pellets, and a lot of hydrologists and engineers that engineer a well will specify that you use these pellets. And so it forms a semi-solid flexible seal, and the permeability 1.0 times 10 to the minus 8 centimeters per second. And like I said, coated and non-coated. Sorry, I'm getting ahead of myself. So inhibited grouts, use light inhibited polymers to achieve working time to mix and place grout. Like I said, in the vadose zone, not good. So we have to keep that in mind when we're using pumpable grouts. So the objective is to maintain inherent properties of the base bentonite. So we want to retard the hydration long enough to get them placed in the annular space. And when you pump grouts, you need to have the proper equipment. Now, I've seen people, I've seen a lot of things, but you have to have basically you have to have a grouter. And grouters are expensive, but if you're in the business of placing grouts, then it's a good investment to buy one, because you run into problems by like maybe not having a really good seal. They're less susceptible to subsidence and loss of formation because they are a size chip, probably anywhere from 30 mesh to 1/8 inch. Definitely not the best for the vadose zone. And like I said, we have to have proper equipment, grouters, that type of stuff, and mixers. And usually they're one and the same. So here we have, probably 17, 20, 23% active solids. And we talked about active solids, that's active bentonite solids. And we could look at different types of solids. If you put a whole bunch of sand in some sort of fluid, that's a solid, right? So we want bentonite solids. And permeability here is 1.0 times 10 to the minus 8. Now we get into dispersed grouts. I'm looking here, sorry. Pardon me for a minute. Timer went to sleep on me, so. Okay, dispersed grouts, formulated using chemical or polymeric dispersants to achieve the ability to mix, pump, and place the grout. The category of pumpable grouts has gained popularity due to demand in monitoring wells. Monitoring wells are definitely smaller, and they have a smaller annular space, so liquid, liquid pumpable grouts are probably preferred. Some water samples taken from monitor wells to test for presence of hydrocarbons. Carrier oils that we normally use to inhibit or to disperse the grout start out. They have a carrier fluid that started life out as an acrylic acid, which is a hydrocarbon. So if you're testing for these in monitor wells, probably not that type of grout that you want to use. Originally, a higher percentage of solids inhibited grouts. We can place it with multiple types of equipment. They have low shear strength. Type of equipment I'm talking about is like Wilden pumps, like an air pump, a buoy pump, a positive displacement pump. they have low shear strength, and they're more susceptible to subsidence and loss of the formation. And definitely not be used in the vadose zone. So most 20 to 30% pumpable grouts are referred to as dispersible grouts. In place, like I said, multiple types of pumping equipment. And totally inorganic additives. A lot of, now this is a little sidebar here. A lot of states, everybody wants biodegradable, right? In your products, whether you're drilling products or your drilling additives. Biodegradable is not good in the water well industry. And like I said, just kind of going off the ranch here. If you use, say, some sort of like an organic fiber, whether it's cedar fiber or it's paper or multiple types of lost circulation material, and there's a lot of polymers that are natural, like guar gums and starches and different things. What that does is that it provides a food source for bacteria in the water in the aquifer. But not all bacteria is bad. Some bacteria is pretty good. But they all like it, and they get happy, and they multiply, and all of a sudden now you'll have a bacterial plume in your aquifer. So that's why everything's organic. You know, it's inorganic because of the bacterial nutrient that we provide to the bacteria in the groundwater. Low shear strength and susceptible to subsidence and loss of the formation because they are liquid, and if you have some sort of a fracture, we have fault or we have whatever, and you'll probably lose that. I don't know why they disappeared in Nebraska, but they did. So, what's that? One more minute. Oh my gosh. I got a lot of material. So anyway, don't use these in the vadose zone. We'll get on to cement here in a minute. 20% and the 30% respectively, 2.5 times 10 to the minus 8, and 3.0. Okay. Pumpable grouts, proper applications, stable borehole environments, saturated zones, no vadose zone, and we'll jump over here, improper applications, unstable borehole environments. You don't want to have bridging going on. Not in the vadose. Highly unconsidered fracture formations, bridging again. Artesian environments, you don't have enough hydrostatic head to keep that contained. Hydrocarbon contaminated zones, zones with other contaminants. Different types of bentonite, chips, pellets, coated, dispersed. Okay, I don't want to rush through cement, but I want to talk about it. Has high compressive strength, resistance to contaminants. I live on the West Coast. I live in Washington, but anywhere you might have an evaporative basin where you're going to have like high chlorides or high hardness. Cement might be a pretty good alternative to using bentonite grouts. Those two contaminants are contaminants for bentonite. They won't allow them to swell. It has a confining pressure. They're high density, so if you have an artesian kind of conditions, a lot of people used to say that cement's that's number one. So it becomes a strong material, 12 pounds per gallon up to 16 or 15 and a half. The thing about cement, heat of hydration, it can collapse PVC. You create microannulus in steel pipe to where it expands it. When it cools, it contracts, and now you have a microannulus. So, filtration control, in other words, you have a hydrostatic head on the cement. It tends to push the water out. Cement has a requirement for water, but there's additives to counteract that as well. Do we have 30 more seconds? Okay.
Yeah, I think we took a few minutes from you.
Okay.
In the beginning, so.
Okay. Cementing water requirements. Quickly, the cement industry came out with a different type of cement other than Portland. They called it 1L. And 1L, basically, the cement, when you create the clinker, it has to go through a furnace. And so it creates this cement minerals. And so what they decided to do, because I call it green cement, you don't run it through the furnace as long, so you don't use as much fuel. So what they do is they reduce that time that's exposed in the furnace, and so the manufacturer will add either 5 up to 15% calcium carbonate dust. And no manufacturer has the same mixture. So some of the cements that we were seeing, these 1L cements were going off, like when we're cementing downhole, we're cementing some mining equipment, mining wedges, other types of stuff. It would go off on us. What we wanted was predictability. So we were having a problem with that. So we rectified that with just a little bit more water requirement than we would use with Portland type 1, type 2 cement. So filtration control additives, you can add it to the cement, doesn't change any of the characteristics, it improves your flowability, and it also reduces your time, giving you better assurance that the cement has gotten down to where it needs to be. And everything, cement, what we don't want is hydraulic bonding, right? We went with the casing and with the borehole. That you guys remember that big fire they had down in the Gulf of Mexico that was improper hydraulic bonding. So basically, we talked about in the beginning, the drilling type of method. If you're when you're drilling, you create what we call filter cake on the borehole. And if that's not removed and you try to cement, then you're not going to get a cement borehole bond. So it's important that you do the drilling process as well, properly as well. So here we go. What we recommend is 6 gallons of water and 94-pound sack of cement. Of course, proper equipment for mixing everything. Always remember the fundamentals of grouting, what we're trying to achieve. We match the grout to the sealing job, whether we have contaminants, whatever we might want to use, cement versus bentonite or a bentonite type of grout. Bentonite seals have limitations, so don't just use the right material for what it's designed for. And the most common reason the seals fail is improper placement, and I would say bridging. And I think that's focus on quality. Some bentonites they're all created different. Like I said, we got the pulse out here in the west. There's other clay deposits around the world, but they're certainly not as good as what we got the luck of the draw. I don't know why. And like I said, successful seal starts before the first turn of the bit. And that's all I got. So are we done?
Yeah.
Okay.